Swayam Prabha. Digital India. Educated India.
First, let's discuss some very basics of computing. So, as you know, the computing stack looks like this. We have the software, which essentially consists of problems, algorithms to high-level language programs. And at the bottom, we have this hardware layer, which is microarchitecture, function blocks, logic gates, circuits, transistors. And in the middle sits our compiler, assembly language, assembler, linker, which leads to the executable binary, and of course the operating system, which is sort of an intermediary between the upper portion and the lower portion. So this is what consists of computer architecture: knowledge of assembly language, microarchitecture, function blocks, and logic. So this is roughly what computer architecture means. And some of you may not heard of the term microarchitecture. So the microarchitecture essentially implements some algorithm, as simple as that. So just the way we implement algorithms in high-level language programs. Similarly, every algorithm describes also a microarchitecture, because every algorithm can be also implemented in hardware. So there is no difference as such between microarchitecture and an algorithm. It's just a one-to-one correspondence. And then the microarchitecture gets implemented in function blocks like adders, subtractors, multipliers, encoders, multiplexers, and so on, which further gets transferred to logic gates, and then those are taken to circuits and transistors. And this is what a computer system looks like. All of us know. At the center, we have this instruction processor or the central processing unit. And surrounding it, we have I/O devices, non-volatile storage, and the main memory, which is the dynamic random access memory. So this is typically what a computer looks like. So the central processing unit, also known as the microprocessor, or simply the processor, dictates how a task will be done, but not do anything on its own. We know that. Needs to be told what to do next in the form of a stream of instructions. And these instructions are generated from a program that represents an algorithm for accomplishing the task. So we know this stuff pretty well. And of course, it can store intermediate or final results of a computation in main memory. So this is the name of the technology used to build main memory, dynamic random access memory, which is typically volatile. And also it can store information on persistent non-volatile storage media like magnetic hard disk, and there are many more today, non-volatile storage media which are better than magnetic. And this is a short list of I/O devices. In fact, this list is incomplete. Any plugin that you can think of that is used for communicating with the environment or the world. Like the display can be of different types depending on the technology. You have keyboard, mouse, DVD reader, writer, speaker, microphone, camera, wireless communication, Ethernet communication, and so on and so forth. So the first thing that we'll try to understand is how does an instruction execute inside the processor. Now, every entity residing inside a computer has an address. That's extremely important to understand. So an instruction also has an address, and the processor maintains the address of the next instruction in a register called program count. That's the name given to this particular location where this address is stored. The instruction is fetched from main memory and placed in an instruction register. The instruction is decoded to generate the control signals for executing the instruction. For example, if it's an addition instruction, you need to send the instruction to the adder, activate the adder, get the work done. So these are the signals that the decoder is supposed to generate after decoding the instruction. Now, most instructions require source operands for execution. That is, what are the values that you want to operate on? Like, if you have A plus B as the operation, then A and B are the source operands. And after decoding the instruction, the operands get fetched, because you have to fetch A and B also from somewhere, right? Operand addresses are typically encoded in the instruction or could be implicit, depending on how the instructions are implemented. These addresses are known after decoding the instruction. So we'll look at some of the details about it, that what are these addresses. And the instruction can now execute once you have the values of A and B with you, and the operands will be sent to the adder will add them up. Okay. That's how the instructions will execute, and most instructions will generate a result, like it could be C equal to A plus B, where C is the result. So the address of the result of the destination operand is typically encoded in the instruction, or could be implicit again. All right, so because you have to remember that everything has an address, okay, so that's extremely important. Now this address is also known after decoding the instruction. That result is stored at the destination operand location. Once you have the address, you can send the result and store it. Now, the execution of an instruction requires appropriate control and data paths to be activated. Just like I said that, so what are the things that we just discussed so far is that the data path involves fetching A and B, the control path involves activating the adder and getting the addition done, and again data path involves sending the results to the destination location. Now the data path is usually slow because main memory is much slower than the processor, much slower. So commonly used optimizations for speeding up the data path involve the following two. First of all, you can have a reasonably large set of general purpose registers inside the processor for storing these values that avoids going to the main memory every time. And you can have fast memory known as cache inside the processor. That also helps you have data inside the processor so that you don't have to go to main memory. So we'll talk about these two things in more detail. So this is what a typical computer today looks like. We have, this is our processor, which is typically SRAM plus logic. What is SRAM? That is static random access memory. So this is again a type of memory technology. And SRAM is typically used for building registers, caches, and any type of memory on chip that you can think of. Right? And this logic part essentially does the operations like your adders, subtractors, multipliers, dividers, and of course the sequencing logic that will actually walk through the instructions one by one. That's also part of the logic. And this chip typically interfaces with a few things. First of all, your memory cards. They look like this. I'm sure some of you must have seen this if you open up the computer. So these are your memory chips that sit in a card. Okay? And they talk to the processor through a DRAM controller. So it's again a small piece of processor embedded inside the processor, which can talk to the memory cards. Okay? And these buses that connect the DRAM controller to the cards are called the DRAM channels. And these channels are extremely important because they dictate, like for example, the width of these channels and the speed of these channels dictate how fast you can ferry data between the processor and this memory. So these are very important. So they dictate the bandwidth of the memory, these channels. How many you have, how fat they are, and so on. Okay. On the other side, you have your I/O devices, and one of the very important I/O devices is the hard disk. So I show that specially. So hard disk talks to this controller, and then there are these I/O hubs that connect to this. So a more detailed diagram would look like this. You have an I/O hub here, which would actually connect all your I/O devices. Okay. So that's more like an I/O controller, which will decode which I/O device you're talking to and so on. I show the disk only here. It will connect to many other things like your DVD reader-write, keyboards, and all these things. So hard disk controller, I/O hub, and then there is something called this DMA controller, which we'll talk about a little bit, which help the CPU transfer data from I/O devices to main memory. So it stands for direct memory access. So we'll talk about that a bit. Now separated out the SRAM cache and the processor logic. Here you can see the interface here also. You have a typically 32-bit data bus connecting the processor logic to the SRAM cache. It could be 64-bit also, depending on how wide the processor is. You have a 32-bit address bus. It could also be wider. And there is a command bus which says whether you want to read or write from the SRAM cache. And since this is on chip, it is quite small in size. maybe a few tens of megabytes. That may not be able to hold all your data. So if you can find something on the SRAM cache, you have to go to the DRAM controller. And there the interface is typically fatter than what you have here. You have a 64-byte data bus. So that's the grain of data transfer between the cache and the DRAM. At a time, you can transfer 64 bytes of data. You have a 32-bit address bus, and you have a command bus which asks the DRAM controller to do a read or write from DRAM. And DRAM controller now translates this to a language that the DIMM cards actually understand. What is this DIMM card? This stands for Dual In-Line Memory Module. So that's the name of the cards. So there are reasons for calling it DIMM. I'll not get into that. And that these commands further get translated to certain other types of commands like activate, precharge, column access, and so on. I'll not get into details of this. This has to do with the internals of the DRAM chip, how to actually access the data inside the DRAM. And of course, you'll have an address bus and you have a bidirectional data channel. I'm showing it as a 64-bit. These channel widths are actually standard. It can be arbitrary. There are few standards for this channel width, like 64 bits, 128 bits, and so on. And why there is a standard? Because these DIMM cards are designed by a certain set of industry, whereas the DRAM controllers are designed by processor manufacturers. So if these channel widths are arbitrary, then there will be a big problem interfacing these two things. So that's why these have been standardized, this interface. You can do arbitrary things here. So this is what the big picture is. So this is what it looks like, and we'll look at some of these elements slowly as we go on. So first we'll look at the instructions in a bit more detail. So what is the instruction set architecture? So let's try to understand that. So I'm sure many of you have heard of this term ISA. So operations of a computer are done through instructions. That's what we just agreed. And one instruction does one operation typically, unless you have a very complex processor which can actually do a lot of operations in a single instruction. Set of instructions supported by a computer is the instruction set of the computer. Right? And organization of the computer defined by the instruction set is the instruction set architecture of the computer. That is, whatever is visible from your instruction set would define the instruction set architecture, like number of registers, number of instructions, the width of an instruction. So that's the part of the instruction set architecture. However, there is a lot that goes beyond instruction set architecture, that is beneath it, which is not visible from the instruction set architecture. And we'll talk about that too. So the guiding principle in designing ISA is that implementation of the ISA should be simple, because that typically dictates how complex your processor is going to be, how complex your compiler is going to be, and so on. The programming language that uses instructions of a computer is called an assembly language. So it's a slightly different kind of language which deals with instructions directly as opposed to high-level language constructs. So very simply speaking, every computer must be able to do arithmetic operations like add, subtract, multiply, divide. So there could be other operations also, but these four are rudimentary. That is very much required. Okay? The variables operated on and the result variables are called operands. The operands used in operation are called source operands or read operands. That is the operands which we read. The operands used for storing the result of an operation are called destination operands or write operands. That's the operand we are going to write to. For example, in C equal to A plus B, A and B are source or read operands, C is the destination or write operand. And most computers allow at most two sources and one destination per instruction. So that's extremely important to keep the design simple. So for example, if you consider the MIPS instruction add A comma B comma C, what it means is that, so by the way, MIPS is the name of a processor family. And what does it stand for? Does anybody know? Sorry? No. No. So, yes? Yes, right, exactly. Microprocessor without interlocked pipeline stages. So, of course, I'm not going to explaining that. So, anyway, so this instruction add A comma B comma C means that add is the name of the instruction, which is often called the mnemonic of the instruction. And among the three operands A comma B comma C, the one right after add is the destination operand. So that's why typically we write instructions. The destination appears after the name of the instruction. So in this case, A is the destination. So essentially what it is saying is that you add B and C, put the result in A. Okay, right? And B and C are the source operands. So far, for example, in the previous example, we have assumed that instruction operands are same as high-level language program variables. For example, A equal to B plus C would translate to add A comma B comma C. Unfortunately, that's not correct. Each hardware operation reads its source operand from some storage and writes its destination operand to some storage. All right? The storage can be either a register from the register file inside the processor or a memory location. By memory, we usually mean random access memory of the RAM of the computer, which is typically built out of dynamic random access memory. And anything that is accessed from DRAM is also copied into SRAM cache inside the processor. Why? Because you may require it in the future, so that's why you copy it into the cache. And if the SRAM cache is already full, then you may have to replace something from the cache. So at any point in time, the SRAM cache stores a subset of the DRAM contents. That's very important. And what subset it stores will be determined by the replacement policy of the cache. That is what you replace to accommodate a new item. The data in a memory location can be found in SRAM cache or in DRAM. And the DRAM is accessed only if the SRAM cache does not have the data. So first you look up the SRAM cache, then you don't find it, you go to the DRAM and access. Okay. Now translating a high-level language program to an assembly language program involves two basic steps. Mapping the high-level language operators to computer instructions, that's the first step. Exact instruction names differ from one computer to another, but the operations done by the instructions are largely same. Like for example, you have add, subtract, divide, multiply, and, or, XOR, this kind of instructions. And the second step is to map the high-level language operands, that is the variables of your program, to computer instruction operands. So these are the basic two steps that a compiler does. Right? The second step requires deciding which variable is stored where and when. Now every variable gets a fixed memory location during the life of a program. However, this forces every computer instructions to operate on memory operands only and obviates the need for a register file. So if I say that, well, in my operation A equal to B plus C, I allocate A somewhere in memory, B in some other location, C in some other location. Now that means whenever I execute this particular statement A equal to B plus C, I have to go and fetch B and C from memory, which is slow as we have agreed, right? So we need a faster storage, and accessing register is faster than accessing memory. So that means we want to store something in registers as well. We want to use a register. So fast access to registers motivates mapping variables to register operands. And the simplicity of design also motivates restricting the operands of certain instructions to registers only. That is, you want to say that certain instructions cannot even access memory. You always want to operate those instructions from registers only. So what is the advantage of doing that? Well, you will have consistent latency of these instructions. Like for example, if you say that add, subtract, divide, multiply, these arithmetic operations will operate only on register operands, then I can easily calculate the latency of these operations. Because memory latency is non-deterministic. How long it is going to take, you don't know actually. For example, in MIPS, many instructions including arithmetic allow only register operands. It doesn't allow memory operands to be in these instructions. Whereas in x86, both register and memory operands are allowed, which makes instruction latency very big and makes the design also complex. Now, width of register file dictates the width of a register operand, which is usually 32 or 64 bits. And this also dictates the width of the data path used in computation. And this also dictates the width of the computer. Like for example, when you say 32-bit computer, this is what it means. It's how wide the registers are. When I say 64-bit computer, this is what it means. It's how wide my registers are. Now, one problem is that as the register file gets taller, that is, as you have more registers, it gets slower and slower. So essentially, that means you cannot have as many registers as you want. The number of registers is going to be restricted. Now, since each variable is given a unique memory location to store its value, that's what we have just agreed, that at the beginning of the program, A, B, and C in your A equal to B plus C will have fixed memory locations for storage. So that means every variable has to be copied to a register if an instruction wants to use it as a register operand. It has to be fetched from memory and put in a register. In MIPS, for example, arithmetic and many other instructions only allow register operands. So there is no other option but to do this. That is, you have to copy the memory operand first to a register and then operate. Now, not all variables of a program can be allocated in registers at the same time because you have restricted number of registers. Variables are allocated in and deallocated from registers as the program progresses. That means they are filled from and spilled into memory. And this is a very important step in compiling a program. So register allocation of variables is the compiler's responsibility, and it's a hard problem as it turns out. And the goal is to minimize the number of fills and spills because memory access is inefficient. So you have to allocate registers in a judicious manner. So I'll show you through an example where it gets tricky. So let's assume that we have 4 registers in a computer, R1, R2, R3, R4. These are 4 registers. And let's try to compile these 4 C statements. A equal to B plus C, D equal to E plus F, A equal to A plus D, B equal to A plus E. So let's suppose that we have allocated A, B, C in R1, R2, R3. So that's what the comment says here. And we can allocate D to R4. The problem is now we have exhausted all our registers. The question is how to allocate E and F. So if you start thinking about it, right, how to allocate E and F, clearly you have to throw away some variables from registers to free up some registers, okay, right? And the question that now needs to be answered is which variable should I throw away? If you look at the following statements here, you can see that A and D have been used here. So throwing away A or D would be a wrong decision, it would be a bad decision because that would require them to be fetched from memory again. A and E are also used here. So this essentially tells you roughly what are the things that are required in future, and these are called live variables. So depending on that, the compiler will decide what to throw away and what to keep. So this is what you can do. So this is a rough translation of those 4 statements. So first, as we said, we have allocated A, B, and C in R1, R2, R3. So first thing we'll do is load B and C. So that's what we have done into R2 and R3. So load means fetching from memory, all right? Load R2 from address of B, load R3 from address of C, all right? I don't need to load A because I'm going to override A. Okay. I'll generate a new value of A, so I don't need to load A. So that's what I do in the next instruction. I generate the value of A by adding R2, R3 and putting the result in R1. So that completes translation of this particular statement, more or less. We have to still store back A, okay, so we'll do that. Then I look at this particular statement and try to compile E plus F. So first I fill E into R2. So I've decided that I'm going to throw away B. And that's motivated by the observation that B is not needed anymore here. I'll only generate a new value of B, but I'm not going to reuse B in future. Okay, so that allows me to throw away B and reuse R2 for E. And similarly, I have decided that I'm going to throw away C because C is also not used in any of the computation. And fill F into R3. All right. And then I can compile D equal to E plus F. I have decided to put D in R4, so that's this one. And then I can do the rest. I have D in R4, A in R1, so I can generate the new value of A here, R1, R1, R4. And I have A in R1 and E in R2, so I can generate the new value of B, which is R3, R1, R2. So that completes the compilation of these operations. Now I have to store back the values that have generated newly, which are essentially, if you look at the left hand side, you'll see I have to store back A, D, and B. These are the 3 things that have been generated here. Okay. So, I store R1, which is A, store R3, which is B, and store R4, which is D, to their corresponding addresses. So this is very fundamental to the compiler design, that what variable gets allocated to which register, and that will clearly dictate the performance of your program. Because if you have a bad compilation, it will increase the number of trips to the memory. So now we'll move on to a bit on processor design. So we'll start with an abstract model of computer. And we'll essentially assume that each instruction goes through 5 stages. So this is roughly based on what an instruction does. Stage 0 is called instruction fetch, where you fetch the instruction pointed to by the program counter from memory. So program counter is the place where you get the address of the next instruction. Stage 1 is instruction decode and register fetch. So this is the stage where you decode the instruction to extract various pins and read source register operands. So this is where you read the sources and get ready for execution. Which is the next step, stage 2, execute the instruction in the ALU, that stands for arithmetic logic unit. Like it will have your adders, subtractors, dividers, multipliers and all. Compute the address of load store instructions. That's also done in this particular stage. So if you want to access memory, you have to also compute the address of those instructions, which is done in the ALUs. And you can update the program counter to the branch target. So for example, if you have an if-else statement where you typically go sequentially, but when you hit an if statement, you have to jump to the else part to execute. So that requires changing your program counter in a non-trivial way. And that's what is done here. So the ALU will first compute the branch target, and then it will update the program counter so that the instruction fetcher knows where to fetch the next instruction from. Stage 3 is memory access. You access a memory of the load store instruction, or and you use the address which is computed here. And the last stage is write back. That is, you write the result back to destination register if the instruction produces a result. Right? So these are the 5 stages. And so what we can do is we can put all these 5 stages in a single logic, which is this cloud here. And it will talk to essentially a bunch of things. The program counter here, our instruction cache, which will store the instructions in a fast memory, our data cache, which will store the data in a fast memory, and our register file, which will store the register values. So if you look at the interfaces here, the program counter requires a clock to essentially keep on increasing the program counter or change it. You go tick, 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 tick at every step, executing one instruction. The instruction cache will use the program counter to access the instruction and send it back to the logic so that it can decode and produce other signals. And the data cache will require an address, will send out a load data, or will require a store data to store something in the data cache. And the register file will have a bunch of ports. So these are essentially the interfaces. Like for example, if you have 2 read ports, essentially there will be 2 connections here. You can send 2 different register numbers and it will give out 2 different register values. For example, A equal to B plus C may require 2 register values to compute on. And also if you want to send out a result and store in a register, you will essentially send the number of the right port. That is, maybe you want to store in register number 23. So you will send 23 here, and the result register file will store the value in the register 23. And if you have a branch instruction, you may have to update the program counter using the branch target. So this is roughly what the processor looks like. So most of the complication actually goes into this piece of cloud. So if you try to look at the performance of this machine, so each stage takes 1 cycle to execute. That's what we have assumed. So a clock cycle comes, the program counter changes, a new instruction gets fetched, it gets executed, and so on. So now what we can do is we can divide each stage into different cycles. So essentially that's called a multi-cycle instruction execution. The processor is now a 5-stage finite state machine. So every stage becomes a state machine. I'll show you pictorially what it looks like. And the memory elements are sequential, so essentially so they will be built out of flip-flops and all. And the cycle time is equal to latency of the longest stage. So one observation that comes out from here is that, for example, in the second cycle, where you are decoding the instruction, right, you get to know the instruction type. So for example, you get to know whether the instruction is a branch or not. If the instruction is not a branch, then I can start fetching the next instruction because I know that the next instruction is just next to the branch instruction. Right? Similarly, when the ALU is doing an addition, for example, the decoder is not doing anything, because we said that one instruction comes in, it goes through all 5 stages, completes, and then we pick up the next instruction again. Right? So clearly only one stage is active at any point in time, and that wastes hardware resources. So a simple way to improve hardware utilization is that you form a pipeline. That is, you process 5 instructions in parallel, and each instruction is in a different stage of processing. So pictorially this is what it looks like. So if my time goes in this direction, that means my cycles are in this direction. Okay. And each vertical column is essentially a cycle. Right? So the first cycle, what I do is I fetch the first instruction, which is I0, and we will go through the 5 stages as usual in 5 cycles. In the second cycle, when I have completed fetching I0, I can start fetching I1. And third cycle, I can start fetching I2. Fourth cycle, I can start fetching I3, and so on. So now, as you can see here, in every cycle, there is an instruction. That is, if you look at the vertical line here, this is one cycle. There is one instruction in each stage of the processor. So ideally, I can finish one instruction every cycle. That's what I can do. So that's essentially called the CPI, or cycles per instruction. So the cycles per instruction of this processor is 1. So I can finish one instruction every cycle. And compared to the previous design, the performance should improve 5 times. Because in the previous design, we were fetching one instruction, and we are waiting until it completes. So the next instruction would have been fetched here after 5 times. So that's the improvement in performance as you pipeline. And today all processors are pipeline. So gains are, you can extract parallelism from a sequential instruction stream, which is known as instruction level parallelism. And you can complete one instruction every cycle ideally. But it comes with a few losses. One is, each 5 stage may get lengthened a little bit due to the control overhead, because you have to put certain registers between the pipeline stages, and that takes time. And so that's why each instruction may take slightly longer. You also require bigger aggregate memory bandwidth. Why is that? So if you go back here, so if you notice in a particular cycle, I am accessing, so every cycle, first of all, I access memory. If you go like this, you notice that every cycle some instruction accesses memory. So that requires the memory to be active more often than the previous cycle. So that requires more bandwidth from it. And there are these pipeline hazards. So let's try to understand what they are quickly. So let's say this is a branch instruction, which you can see here 5 stages: fetch, decode, execute, memory write. And the branch instruction executes here. That is, it computes where to go next. Right? The problem is that in these 2 cycles, you don't know what to fetch. You will get to know what to fetch only here, once the branch is executed and computed the target. You can transfer that to the fetcher here, and you can fetch the target. So what do you do in these 2 cycles? So if you do nothing, then essentially that will lead to wastage of 2 cycles every time you execute a branch. And these are called pipeline bubbles. That is, it looks like nothing is moving in the pipe. There are 2 bubbles going. Right? And that increases the average cycle per instruction, because as you can see here, every branch instruction now introduces 2 bubbles into the pipe. So I'll not get into the solutions for this, but very quickly, today all processors rely on something called branch predictors. So what are they? Well, looking at the past behavior of a branch, it tries to predict where the branch target is going to be, even before the branch executes. Right? And the good news is that the branch predictor accuracy today is typically higher than 97-98%. So it's extremely high, extremely predictable. But there are branches which are notorious. So essentially that means I can actually predict the target and start fetching from the target, hoping that it's correct. And given that the accuracy is very high, the probability of being wrong is low. So, but of course, if you make a mistake, that means whatever you have fetched here will have to be thrown away. And the processor must restart from the branch branch target after throwing away whatever you have fetched. So that's called a pipeline hazard, which involves a branch instruction. So there are other types of hazards as well. So if you look at this instruction sequence, this instruction adds $2, $3. So these are register names. Instead of R2, R3, I'm using $2, $3. Puts the result in $1. Subtract uses $1, and uses $1, or uses $1, XOR uses $1. So all these instructions depend on the add instruction here. Okay. So now if you look at the pipeline, this add instruction will be fetched here, decoded, executed. It will not access memory, but it will go through this stage doing nothing. And then we'll write back the result of this add instruction to register 1. The problem is that the sub instruction here will read its source operands here in this particular cycle, which also includes $1. And clearly it's going to be the wrong value, because $1 is not yet updated, it's updated only here in this particular cycle. So similar thing will happen with the AND instruction or instruction. So it's called a data hazard. That is, you are unable to deliver the data to your instructions because of pipeline. So fortunately there are easier solutions, and the observation is that this instruction actually has produced the result here, even though it hasn't yet updated $1. Because the moment it crosses this particular stage, the result is available inside the processor. And this instruction requires the result of this instruction only here, which is sort of slightly future in time. So that means I can transfer the result from here to here and do the computation correctly. So that's what is shown here. So these are called bypass paths, which are implemented inside the processor. And these paths are activated after detecting a hazard, so that you can actually execute all these instructions correctly without any problem. So the observation is that this instruction will read a wrong value of $1 here, which is okay, no problem. We are going to override it using the result of this here just in time. So the processing pipeline will proceed without any problem. Unfortunately, you cannot do this all the time. So there are places where you have to introduce stalls and all. I'll skip this example, which shows why you have to introduce stalls. So essentially, hazards can cause pipeline stalls and introduce bubbles in the pipeline, depending on the pipeline organization. And overall speed up of pipelining over multi-cycle non-pipeline implementation is number of pipe stages divided by 1 plus the average stall per instruction. So this is the ideal speed up, number of pipe stages. As you make the pipe deeper and deeper, it should give you better and better performance. But this term here gradually eats into your speed up. So because typically as the pipe gets longer, these stalls become more and more. All right, so again going back to our previous diagram of processor. So now we can see a little more detail. So this is essentially the state machine which we just talked about, 5 states going through one by one, fetch, decode, execute, so on. And we have our ALUs also here in this logic. So a little bit about the ALU. It's responsible for executing the core of the instructions, everything except memory operations, loads and stores. Typically the ALU takes 2 inputs for most instructions and produces a result that may or may not get written to a destination register. For example, branch instructions produce a branch target, which doesn't go to a general purpose register but goes to the program target instead. Right? So that's a slightly different type of ALU instruction. And ALUs are typically of 2 kinds, integer and floating point. The floating point ALU is often referred to as a floating point unit. So most of your HPC programs would actually exercise the floating point unit because they do a lot of floating point operations. But I'll not get into the details of this, what goes inside that and so on. All right, so now what we'll do is, how are we doing? Okay. We'll try to spend a bit of time understanding caches and a bit of virtual memory because that sort of plays a big role in performance. And if you ask me, I would say caches are probably the biggest innovation in history of processors in terms of performance. Okay, so this is what we're talking about. Cache here, sitting between your processor logic and the DRAM controller. So the first, there is something called locality principle, which dictates the design of caches. And principles of locality that are executed by the programs are essentially come in two flavors. There are two types of locality. One is code and data accessed now are likely to be accessed again in the future. So that's one type of locality. That is, if I'm accessing a certain piece of data now, it's highly likely that I'll require it again in the future. Right? So any interesting, and why is that? Because any interesting program could have loops and or recursions. So whenever you put loops or recursions, that means you're doing something repetitively. And anything done repetitively may have this kind of locality. That is, whatever I'm working on now, I may want to work on that again in the future. So, so that justifies why code and data accesses may be repeated. Here's a very simple example. If you're multiplying two matrices, let me see if I can use this one. So if I have two matrices, so as you know, to compute one element of C, what I'll do is I'll take one row of A, one column of B. I'll take the row of A and column of B and multiply and get the first element of C. To get the next element of C, this one here, I'll take the next column of B, same row of A, right? So you can see here the rows of A are getting reused, right? Similar thing is going to happen regarding column of B. When I go and start working on, for example, the next row of C, this element, for example, we'll take the next row of A, the first column of B. So rows of A and columns of B are getting reused, as you can see here. Okay, so that's what is mentioned here. The reuses. So this is essentially called temporal locality. That's the name of the locality. That is something that is I'm working on now may require again here. The second type of locality is that code and data allocated close to the code and data being accessed now are likely to be accessed in the near future. What does it mean? That means, let's say I'm working on a particular vector, right? And let's say I'm working on the element, the ith element of the vector. It's highly likely that I'll probably require an element close to the ith element. It may not be I plus 1 or I minus 1, but maybe close to that. Okay. So that's the typical nature of computation, that we have a domain locality around the element that we are now currently working on. So this is in fact more prevalent than temporal locality, and it comes from, for example, sequential code access. I typically go over instructions one by one sequentially, so that leads to this kind of locality. Also, sequential data access. For example, if I want to walk over an array, I mentioned that, for example, if you want to reduce a particular vector, that is adding up all the elements, typically you would go over sequentially the vector and add them up. That would also lead to this kind of locality. This is called spatial locality. All right, so these are the two kinds of localities seen in the programs. And our caches exploit these two principles when they are designed. So, so locality principles imply an important corollary. And what is that? Programs usually work on a small portions of code and data at a time. Since we are saying that whatever I'm working on would be needed again, it cannot be that my execution would spread over a large amount of data. It must be, confined to a locale. So that's what is said here, and this plays the key role in design of caches and why caches are so successful. That's because we typically work on small pieces at a time. So the code and data needed over a time window of length t could be a subset of the code and data needed over a bigger time window of length t prime. That's what it means. And if you think about a nested loop, it will become very clear why that is the case. And this corollary is exploited to build a hierarchy of memory and storage structures. It most recently used code and data close to the processor because this is needed now. keep increasingly larger supersets of code and data gradually away from the processor, because they are not needed now but may be needed in future. So whenever needed, I can bring them close to me. Now the obvious question that needs to be answered before we can move on is, why not have everything in a large on-chip SRAM cache? Because that should be my dream. I don't want to talk to the slow DRAM ever. Well, yes, it's possible, we can do that. Nothing is impossible, but only problem is that, first of all, it's going to cost a lot. SRAM is expensive to build, it takes up area, and it gets slower and slower as it gets larger and larger. There are certain principles from electrical engineering that plays here, and it becomes slower and slower as it gets larger and larger. So you can't do this. You can't keep everything in a large SRAM. So memory and storage parts are usually arranged in a hierarchy. SRAM caches are closest to the processor logic, smallest in size and fastest. For example, total on-chip cache is usually a few tens of megabytes today. Varies a lot. DRAM is outside processor chip, much larger in size, much slower than SRAM caches, and typically tens to hundreds of gigabytes in size today. We are hitting terabytes of DRAM. We are seeing servers having terabytes of DRAM. Hard disk holds everything, non-volatile, very large, very slow, and it can be tens to hundreds of terabytes in capacity. So this is a typical storage hierarchy that you can see. Now, hierarchical organization allows very fast access to a small subset of code and data needed now from the SRAM cache. Later, this code and data can be exchanged to bring something else from DRAM. Because as you know, a time will come when you don't need that subset anymore into a different subset of code and data. So you have to exchange this subset with some other subset and bring them from data. So SRAM caches are finite capacity, so something must be replaced to bring something new if the cache is already full. So we replace. Also, code and data in DRAM can be swapped with something else from hard disk on demand, because DRAM is also finite in size, hard disks are bigger, so same principle applies there also between DRAM and hard disk. So this is what happens pictorially. So this is our five-state machine, as you can see here: fetch, decode, execute, memory, write back. And here are three storage elements: SRAM cache, DRAM, and hard disk. I'm not showing the register here. That will be accessed here and here. It will write back and fetch. So let's see what happens. So our SRAM cache is accessed from two states. One is state 0 and another one is state 3. State 0 accesses it because of instruction fetch coming from, here the address is program counter. Whereas here for data access we send the nodes to address, to the SRAM. So what will happen when we access that? Well, let's assume that the number of accesses is n. A fraction of that will come back, because typically the cache won't be able to deliver everything. So let's say a fraction x is found in the SRAM and returned to the processor, and that takes time t1. The remaining fraction will go to DRAM, that is n times 1 minus x, because they were not found in this particular cache. And the DRAM will be able to supply only a fraction of that, because DRAM also doesn't have everything. So we assume that that fraction is y, and that would be forwarded back to the processor, and let's say the total time taken round trip is t2 in this particular case. And whatever the DRAM could not supply will be forwarded to the hard disk. And hard disk should be able to supply everything. So it returns back to DRAM, DRAM forwards that back to SRAM, and the SRAM forwards that back to the processor. Let's assume that the time taken here is t3, the round trip. So one thing to keep in mind is that when something is returned back, that is also filled in that particular level. For example, this amount of data, which was not there in DRAM, when it comes back from hard disk, it will be filled in DRAM. So not that DRAM will not fill it and just forward it. Okay? Because next time it's very likely by the temporal locality principle that next time you will be requiring this again, this chunk of data. This time, and at that time you should not be able to, you shouldn't have to go to the hard disk again. You should be able to deliver it from DRAM. But again, when the DRAM forwards it, the cache will fill it actually. Right? So next access should be extremely fast to this chunk of data. Okay? So one thing to keep in mind is that, as you can also probably guess, that T1 is going to be much less than T2, much less than T3. Because T1 was the time to get something from the cache, T2 was the time to get something from DRAM, and T3 was the time to get something from hard disk. So here is what we have just discussed. Suppose a program's load store instructions and instruction fetcher generate n memory accesses. Nx accesses find the requested data in on-chip SRAM cache. It times 1 minus x times y accesses find the requested data in DRAM. Remaining access fetch the data from hard disk. An access to SRAM cache requires time T1. That's called a cache hit. That's the technical name used. An access to DRAM requires time T2. That's the cache miss. And access to hard disk requires time T3. That's called a page fault. That is, whatever you're looking for in DRAM is not there in DRAM. Right? So you can actually compute the average access time per data item, and that will turn out to be this: nx T1 plus n times 1 minus xy T2 plus T3 divided by n. And if you look at this expression carefully, you'll find that since T1 is much less than T2, much less than T3, as x and or y increases, the average access time goes down, which means I want to have more hits in my cache. I want to have less page faults in my data. So these two are the most fundamental things that I want to exercise when I design my cache or my data. So let me skip this. Okay. So let me skip over these things. Time. Okay. So caches, what do they look like? Okay. Let's try to take a look at it quickly. So typically, what we do is we divide the elements in the cache into hash buckets. So essentially, our cache is a hash table. So these buckets are called sets. So every cache has a set. Right? So a bunch of sets. Essentially. So here, for example, I'm showing a bunch of sets here. Sorry. So whenever a data item comes, it is assigned a particular set to some hash function. And as you can see here, in a set, in this particular case, there can be two hash elements. It can sit here or here. So you can choose whichever place it wants to sit in. And number of hash elements in a particular set is called the associativity of the cache. And you can increase it if you want. In this particular case, I have a two-way set associative cache because there are only two possible hash elements in a particular hash function. So that's what a typical cache looks like. Let me skip over this. Okay, so what dictates cache performance? As we said, we want to have more hits in our cache. So hit rate is an important parameter for cache performance. It's the number of hits divided by number of accesses. That's called the hit rate of the cache, and bigger the better. I typically want, ideally I want 100% hit rate in my cache. Everything is found in the cache. And the miss rate is number of misses over number of accesses, which is 1 minus the hit rate. That you can easily see here. And I want the miss rate to be as small as possible. Average memory access time is hit/miss detection time, because when you look up the cache, it takes some time to figure out whether a particular element is inside the cache or not. That is this particular time, hit/miss detection time. Plus, if you miss in the cache, the miss rate multiplied by the miss penalty is how much time it takes to bring the data from the next level of the storage hierarchy to the cache. So that is your average memory access time. And as you can see here, decreasing. So there are three terms here. One is this hit/miss detection time, one is miss rate, one is miss penalty. And decreasing any of these three terms would improve the average memory access time. And miss rate times miss penalty is often referred to as the memory stall time. You will probably encounter this term in the rest of the lectures. And overall execution time is CPU time plus the memory stall time. So as you can see here, we want this to be small, memory stall time. I want the CPU to be busy all the time. So one important thing is about the caches is that all commercial processors have 2 or 3 levels of SRAM cache on chip today. So now essentially what you're saying is that you not only have this kind of a hierarchy of storage, we are now further breaking down this particular blob here into multiple caches. All right. So and the reason is exactly the same. The same reason why we have this storage hierarchy gradually getting bigger. The same principle dictates that I can further divide my SRAM cache into multiple levels of increasing capacity. So, L1 is the closest to the processor, that is the L1 cache or the level 1 cache, and L2, L3, etc. are farther away. So today, typical high-end server processors have 4 levels of caches: L1, L2, L3, L4. And as you go away from the processor, they get bigger and they get slower. For example, today typically the L4 cache, which is not built out of SRAM but actually built out of DRAM, is of a few gigabyte size, the L4 cache. Whereas our L1 cache is typically few tens of kilobytes. Right? So the levels are designed such that the latency of fetching a block from the last level SRAM cache is still much smaller than fetching from DRAM. Otherwise, you have no utility of having a cache. So here are the typical parameters of a multi-level cache hierarchy that we find today. Typical sizes are L1 is typically less than 100 kilobyte, L2 is typically less than 1 megabyte, and L3 is typically 2 to 32 megabyte. And all these things are on chip, they sit on chip. Right? Associativity typically increases with increasing level. Block size may increase or may remain constant. Block size is essentially the amount of data one cache element can hold. Typical round trip latencies could be L1 is typically less than 1 nanosecond, L2 is about 5 nanosecond, L3 is about 10 nanosecond, and DRAM is about 50 to 100 nanoseconds. You can see the jump there from L3 to the DRAM. If you have nothing in between, then essentially this is the last stop where you can do something smart. All right? So that's why the design of L3 is extremely important and is a hot research topic even today. That is, how do you actually manage the contents of the L3 cache so that you don't have to go to the DRAM so often. So missing in the last level cache is highly detrimental for performance. So you have to design your L3 extremely judiciously. So that's your multi-level cache hierarchy. Let's see. Here I can. Okay. Let's spend some time on virtual memory. So as you know, the virtual memory gives an illusion of bigger memory. That's what we have learned over time, because every process sees a larger amount of memory. For example, if I have a 32-bit virtual address, a 4 gigabyte virtual memory would be given to every process that runs in the system. And the problem is that today actually we have a lot of memory in our system, so we don't need this illusion anymore. But if you don't have virtual memory, what happens is that you typically be loading the whole program at the beginning, and that will not allow the other programs to run on the memory, because your program will take away unnecessary amount of memory from the system. So virtual memory is not needed today for this illusion anymore, but actually to support multiple different programs running concurrently in the system. That's the main reason. And virtual memory requires a virtual address, because it's a memory, it requires an address. And if you assume a 32-bit virtual address, then every process sees a 4 gigabyte memory. And what is a process? A process is something, is essentially a program. So a program, when that runs, becomes a process. Okay? So that's the technical name used for a running program. So, so every process sees this 4 gigabyte of virtual memory, which is much better than a 4 gigabyte of physical memory shared between multiple processes. Now, to manage the virtual memory, typically it is divided into smaller parts. And these are called pages or segments, or you can even have segments and pages simultaneously. Okay? So let us focus on only paging in virtual memory. That is, let's say that your virtual memory has been divided into smaller parts, which are called pages, smaller equal parts. So entire virtual memory is divided into small units called pages. Virtual pages are loaded into physical page frames as and when needed. That's called demand paging. It means I don't really bring everything that I require at the beginning. Right? What I do is whenever I need something, I'll bring that portion to my physical memory. That's called demand paging. So similarly, physical memory has to be divided into page frames so that a virtual page can fit into a particular page. And the processor generates the virtual addresses, but the memory is physically addressed, so you need a virtual to physical address translation. So this is what it looks like. So if I have, let's say this is my virtual memory, I divide it into pages. And the physical memory may be smaller or larger. It has no relationship with the virtual memory size. Let's say we have a smaller physical memory. I'll divide that into same equal number of parts. Okay. That's the physical memory. Now virtual pages will be mapped to physical page frames at runtime. For example, this could be placed here. This could be placed here. This could be placed here. So on. So essentially what it means is that this translation, this virtual address to physical address translation essentially needs to establish this mapping between the virtual page number and the physical page frame. So the virtual address generated by the processor is divided into two parts. One part is called the page offset, another part is called the virtual page number. So for example, if we assume a 4 kilobyte page within a 32-bit virtual address, then the lower 12 bits will be the page offset, because that will tell you where inside a 4 kilobyte page you are looking for your data. And the remaining 20 bits will be virtual page number. That will cover about 1 million virtual pages. So 1 million virtual pages, 4 kilobyte pages, that will make up the 4 gigabytes of virtual memory addressable by 32-bit virtual address. Now the page offset remains unchanged in the translation, and you need to translate the virtual page number to a physical page frame number, as I said. So where is this virtual page placed in the physical memory? And this translation is held in a page table resident in memory. So as you can see now, essentially you require two memory accesses. First you have to go and access the page table, and then you can go and access your actual memory. Right? So that doesn't look very good. So to avoid this, there is something called a TLB, the translation look aside buffer, which sits inside the processor. And the job of it is to hold the recently used page table entries. And here also again your locality principle applies. That you are essentially saying that if I am accessing the page table, this particular page table entry now, it's highly likely that in near future I'll be accessing the same page table entry. And that's why I want to cache it inside my translation look aside buffer. So this is inside the processor, very fast, just as fast as your caches. And if you can find the translation in your TLB, then it's a TLB hit. You don't have to go to the page table to fetch it. But if you miss in TLB, then you have to go and fetch it from the page table. So this one we have already discussed, the memory operation latency. So what happens actually is that if you miss in the L3 cache, the processor, if you look at the processor, what is it doing actually when you miss in the L3 cache? Well, it is just waiting for the data, right? Because you are looking for some data in your cache, it is just waiting for the data. Now inside the processor, there is a P4 queue which holds all the instructions. So let's say it holds all the instructions that have been fetched. This is called the reorder bar. and it's of finite size, the reorder buffer. So when you miss in your L3 cache, it will take a long time to get the data from your memory. In the meantime, the processor is continuously fetching from the instruction stream. Eventually, this particular queue fills up completely. And now the processor stops fetching. Now, if you try to calculate that how quickly it can fill up, so typically today, size of this reorder buffer is mode bit. So there is a mode bit which is on when on, says that you are inside the kernel, you're executing some kernel process. If the mode bit is 0, that means you're executing a user process. And each process has its own text, data and stack regions. Text is the code, and the data typically consists of your dynamically allocated data and the global data, both of these. And the dynamic allocated data would go into the heap. That's the technical term used to designate the area where your dynamically allocated data resides. And typically the stack and the heap will grow in opposite direction. Typically the stack grows down, heap goes up, and if they ever collide, you're in big trouble. All right. So typically at that time you get segmentation faults or something of that sort. For example, I'm sure if in your life you must have written at least once a recursion program without the terminating conditions. Okay. So eventually you will see a segmentation fault. That's when your stack and heap actually collide, and the program essentially crashes. Right? So anything that is needed to reconstruct the state of the process is in the process context. That's a technical term used. So what are these things? The processor registers that we have discussed, okay, they are part of the process context. Text, data, stack regions in memory. Various kernel data structures such as list of open files and their seek pointers. The process control block is a kernel data structure that maintains all information pertaining to the process context, including the current state of the process. So this is what essentially is technically called the context of a process. Okay, all these things together. Right? So the process control block entries start off as invalid for a newly created process. The process enters the ready queue by linking its process control block to the tail of the queue. And the ready queue is a linked list of PCBs or processes that are ready to execute. So that's the name of the queue, where you keep all the processes ready to execute. On transition from executing to sleep state, the PCB is used to remember the process context by maintaining a pointer to the memory region holding the saved registers and other context information, and a pointer to the process region table. So let's try to understand what is this saved registers and all these things. Right? Let's switch to. So a process has a single thread of control typically. This thread refers to the sequence of instructions executed by the process. A fork call generates a new thread of control, and the question now is it a thread or a process? Often they are used interchangeably, but historically a thread refers to a piece of code in execution and is part of a parent process. So thread is typically much lighter weight than a process. Right? A fork actually creates a process, not a thread. So here are some terms which you'll probably encounter in the rest of the course. Multiprocessing refers to executing independent or communicating processes simultaneously or in a time-shared manner. The term, so essentially this is a general term used to describe a scenario where you have multiple processes. Multi-threading refers to executing possibly dependent and or communicating parts of the same process simultaneously in different threads of control. So as I said, a thread is a part of a process. So, multi-programming refers to executing independent programs in different processes simultaneously. So here this independent is very important, distinguished from the remaining. Entity called process scheduler, which we'll discuss next. Which is responsible for deciding what process to run next. And it's usually not aware of these dependencies that, maybe you're running a multi-threaded program where different threads have a dependency, but the scheduler is not aware of this. So the scheduler essentially just looks at the processes or threads waiting in the ready queue and picks up one and runs it on the CPU. Okay? So let's look at this scheduler a bit, and then we'll stop. So every process in the ready queue can request CPU cycles for execution because it's ready to execute. An algorithm must select one process per processor for execution. This is the scheduling algorithm. And there are two types of process schedulers. One is called a short-term scheduler and the other one is called a medium-term scheduler. And we'll discuss here only the short-term scheduler because that's what is important. A short-term scheduler selects one process from the ready queue for execution, invoked whenever the currently executing process enters a sleep state, because maybe it wants to do something which is going to take a long time, like reading a file, or is waiting for some input from the keyboard, or encounters a timer interrupt or terminates. So timer interrupt is something which comes periodically. Okay. So for example, there is a fixed timer interval which is programmed by the operating system, and every such interval a timer interrupt comes. And whenever this interrupt comes, the currently running process will have to be rescheduled, and the kernel will do something and may reschedule the same process or may schedule a different process. And this scheduler decides the overall utilization of the CPU, because the process you choose determines how well the CPU gets utilized. So let me skip this. Go to the, yeah. Yes, the process scheduling is the activity of selecting the process that will run next on the CPU. Now, whenever you switch the process, you have to save the context of the currently running process. And saving the context means the context we just defined, right? The processor registers. But we don't save the memory context, because the virtual to physical address translation is unique for every process. So whatever is in the physical memory for process A cannot be touched by process B. So it remains there. But you have to save the processor registers, because the registers are going to be used by the new process that will start running. And so it saves the context, selects the process from the ready queue, and restores the context of the selected process, because the selected process may have been was running in the past and may have been rescheduled at an earlier point. Now it comes back, so it has to restore the context also. And the scheduler can be invoked in 4 possible circumstances. One, the current running process goes on a long latency system call, that is transitions from running to sleep state. A new process is created, or a process completes a long latency system call, that is a process transitions from created to ready or from sleep to ready. Third, the current running process terminates, so you have to pick somebody to run. And the fourth, the current running process receives a timer interrupt. So these are the 4 scenarios. The first and the third, that is this one here, transition from running to sleep or running process terminating, they lead to something called non-preemptive or cooperative scheduling. And the term comes from the fact that you're not forcing the current running process to leave the CPU. Right? It just gave up the CPU because it cannot use the CPU anymore. Whereas in the second and fourth case, that is this one where a process transitions from created to ready or sleep to ready, or there's a timer interrupt. In this case, essentially you are switching the process forcibly. It is not giving up the CPU. The current running process can still continue running. Okay. So this is called preemptive scheduling. And so these 2 terms are important to keep in mind, non-preemptive and preemptive. So maybe we can stop here.
Does anybody have?
Yes. Yeah. Typically, the order of milliseconds timer interval. You're talking about the timer interval?
Can you hold the mic closer?
Yes. Yeah.
Because if the timer interrupt
Correct.
is very frequent, then it will context switch a lot.
That's right. Yes.
And how does the OS decide it? I mean, is it fixed for a particular OS, or is it a dynamic for decision?
How is the OS decided?
So the timer interrupt, you mentioned that the OS will decide.
Oh, duration. Oh,
duration.
yeah. No. Yeah. So there is a methodology to pick the timer interval. Typically, you'd look at representative set of workloads and see typical durations for which the CPU is used at length. And from the statistical distribution of that, you typically come up with a timer interval.
With the dynamic.
No. This is done offline completely. Once it is programmed, it's not changed.
Thank you.
Can we dynamically change the interrupt timer interval?
That was the question. Yeah, you can do that, but today no commercial.
Using
Sorry?
We want to use some new algorithm
Yes, you can do that.
based on the history of the how it is being processed.
Yes, you can do that. Possible? Yes, you have to change the scheduler. Yes, here is a question.
What if the virus acquires the timer?
Sorry, second?
What if the virus acquires the timer?
A virus requires the timer. Meaning?
Means what if the virus acquires the timer? Timer is hardware.
Well, acquires the timer. So you're saying that the virus starts changing the timer. So then there will be a lot of problems.
So, but that in normal systems we can manage. But what if in the the professional systems and all, if the virus acquires the timer, there will be a lot of issues. How do we
Yes, even in a normal system, how do you manage?
like normal personal computers? Okay, it's okay.
Yeah,
That is
right.
not a
Yes.
But like our machines in the labs and all,
Yes.
it can be leading to a big issue. How does it work?
Oh, definitely it's going to lead to a big issue. Yeah, so you have to protect your machine against viruses and all. Yeah. More, yeah, here there is a question.
Sir, so at one point of time you told that x86 supports memory operand. So what would be the reason of supporting memory operand? Like if we,
Oh.
if it,
So let's suppose that you want to, let's go back to that C state, A equal to, and let's say B and C are in memory, right? So an x86 instruction will generate a single add instruction, which will add the memory operands, put the result in the memory. A MIPS instruction, MIPS computer, would generate several instructions. First instruction will load B into a register. Second instruction will load C into a register. Third instruction will do the add. Fourth instruction will store the register back to A. You can see 4 instructions. So main advantage of is compaction of the code. So if code is more
the variable latency of instruction could lead to major problems. Like
major problem in the sense your design will be very complex. Yeah.
So like how the number of ports to register file is decided. Like if you would have a lot of ports, then it would become very
Slow. Yeah. Yeah. Right. Yes.
how that is decided.
Again, the common case is that 2 sources, 1 destination. And if you find that your computer, let's say, requires executing 4 instructions in parallel, then that would require 8 read ports, 4 write ports. That's how it is decided.
So, is it a good idea to use the RISC file on the HPC?
Disk 5. Yes, why not? Why do you think it's not a good idea?
It's not that much capable of parallelizing and
No, why does RISC-V is just an instruction set. Why should an instruction set be capable or incapable of parallelizing something?
is it a good idea that we
It's a very good idea. That's all I can say. I mean, as good as any other instruction set. Yeah, in general, I'm a big fan of RISC. So.
Sir, we discussed that increasing the cache size will reduce its increase the latency, and you said the electrical engineering dictates that. But cache is one chunk of memory, right? Whereas registers are discrete memories. So also we discussed that increasing the number of registers will make our system slow. Can you please explain why increasing the number of registers will make it slow?
No, I won't explain. See, very simply speaking, what happens is that the way the register file is designed is essentially a column of bit sets. Okay. So that's essentially 1 bit of, let's say if you have 32 registers, you'll have a column of 32 bits. And if you have width is 64 bits, you'll have 64 such columns. All right. Now, the way the register access works is that there are these wires which span this whole length of a column, and at the bottom you typically have sensing circuits which would sense the values of the registers. as you increase the number of registers, the wire length actually increases. And to charge a particular wire to a particular voltage, you have this RC delay. And as the length increases, the capacitance increases, the resistance increases. So this is a very brief answer at a high school level. So otherwise you have to understand the exact circuitry of the register file and then you can see clearly actually. So both are bad. Increasing number of registers, increasing width of a register. Okay, that's all. Thank you.